Hello everyone, my name is Mabu, Manaileng. I do some AI research at a data science startup called Data Wizards, and today I'll be taking you through some ideas on how you can sort of take ideas coming out of some technical research paper, really iterate on it, apply your own data, and find yourself in a position where you have a model that's ready to go to prod. And the intention of the talk is just to sort of persuade you into believing that if you do enough research and have a good appreciation of what the research paper is doing, the time it takes into converting that into something that you can, a model that you can build that serves customers and stuff, can be very reduced because of the nature of open source models these days with pre-training and other things, and also open source frameworks for deep learning and other wrappers that really make it easy to retrain or train from scratch. This is like very complex model that comes out of research. So my outline is as follows. I'm going to just take you through some papers as examples to say what paper did what type of thing, but this is not a review. The talk is not a review of papers that made an impact in NLP. So obviously I've left a bunch of things that are super important in there, but it's just to sort of show you an example of how a paper can come out and really make an impact in the research community. And that impact in the research community translates to what companies do in production and other things. And I'll also just try to paint a picture of how hard it is to sort of train really deep, large scale production scale as well, production grade deep learning models, and why it's important to go into things like transfer learning and how open source frameworks and wrappers and other things can also sort of try to help you accelerate that journey. And I'm going to give an example of a very NLP specific transfer learning techniques and how you can take advantage of models that come out of that. And I'll show you some Python code as a demonstration of how small, how neat, how precise the code has to be for you to really start iterating over different ideas that comes out of research and building models that can be very ready very quickly to serve customers. So most of you would remember ImageNet as a start. I mean, ImageNet really changed the computer vision industry. The image processing industry sort of really changed after ImageNet came out. First the database, and then obviously the challenge, which Jeff Hinton and team later sort of demonstrated as well, that neural networks can be highly competent. I mean, and then they can sort of outperform other techniques. And that sort of shook the whole computer vision industry, and it has never been the same ever since, to be honest. And obviously in the NLP space, it took a bit of time, but we've had a similar revolution, if you like, and things like Github that introduced pre-trained embeddings and other things sort of really made an impact in changing how we view NLP and how we can very quickly train new language models and models that we can use across multiple tasks. And obviously Clove also tried to sort of take advantage of what the whole Github sort of introduced as pre-trained embeddings, and sort of democratize how you can download those weights and just start using them in your production pipelines. And obviously there's other pre-training techniques that we introduced, especially from this paper for semi-supervised sequence learning, where it was demonstrated that you can very easily take a large corpus of text and in an unsupervised fashion train a left to right type of model that can learn to predict the next sequence, and then use that learning to initialize the weights of an upstream model that you're training. And that worked very well, and obviously a lot of people have been using that since. But attention is all you need also gave us the transformer architecture, which also revolutionized the NLP space. Most people stopped doing stuff that they were doing in like sort of recurrent neural net with LSTMs, and sort of tried to take advantage of the transformer architecture with attention and left to right attention as well. So yeah, and then you'd remember what GPT did from OpenAI, which was sort of the story that exploded about this language model that could generate news that people wouldn't know it came from an algorithm. And then there was a big fuss about how should it be released, and OpenAI took like some phased approach of releasing their very large 2-point-something billion parameters later. And just how this paper was able to allow people to really start doing like some awesome stuff in NLP in the context of language generation. But of course there was the almighty Bert which BERT came out, and then obviously it shook the NLP industry as well. And even today, we still have like some variations of BERT that are all based on the principle of BERT, which is the bidirectionality, obviously, because I mean, it's not very different from the other things, except the fact that they train it in a fundamentally a different way from other generative language models. And BERT in itself is not really a language generator, but it can be sort of adapted to do that. But when BERT came out, people really started changing their mind about how they're going to train their language models, and that turned out to prove to be very useful and to be superior. And obviously then companies like Hugging Face also demonstrated the fact that the fundamental problem with the size of the models and the hindrance in us taking them to production, let alone taking them on edge, because I mean edge machine learning is also becoming a very big deal, but now we can't take this very huge and large models into mobile phones or Raspberry Pis or whatever it is that your edge infrastructure is looking like. So then they introduced the whole concept of learning from the bigger models. Well, they just use the technique, a commonly known technique called knowledge distillation, where you have sort of a teacher and a learner model and a student model, and then the student sort of tries to replicate what the teacher is doing, and the student turns out to be much smaller, and in most cases the accuracies that you lose are minuscule, which is also very powerful in terms of how quickly we can be able to reduce the size of this model so that they can be as production ready as possible. So this is a demonstration, for example, when people release these models, this is just a demonstration of what happens, what goes into training them to allow them to beat like the latest sorter. And it really takes a lot. I mean, if you look at this graph on the left axis, we actually have the number of parameters in the model, and this is just the timeline of what happened when. But you can see that we've been on this trajectory of increasing the number of parameters in the models, and that's why we keep beating the sorter, because it's been demonstrated. I think OpenAI released a paper showing that these models really, when you feed them more data, they just become better. And this is a demonstration of that. I mean, Megatron from NVIDIA was sort of a very large language model, and then we were thinking, I mean, like, wow, so many parameters. But Microsoft Turing natural language generation came out, and it just smoked everybody in terms of the number of parameters, and they also claimed to beat the latest sorter. But you can see down there that Hugging Face's parameters are really small on the DistillBERT model, and this is the whole concept of knowledge distillation and teacher-student models that can allow you to really reduce the weights. I mean, the size of the weights and the size of the model in general, so that you can take it to edge, you can take it to production quicker, because then you don't need like crazy TPUs or crazy GPU time when you're in production. And that's the whole point, because really these models are very data hungry, they're very compute hungry. I mean, GPT-2 alone was trained on like 8 million web pages. And that was like 40 gigs of text data, that's 40 gig. And that's actually nothing. I mean, BERT was like 1.5 billion words, and Roberta, which was robust BERT, a variation of BERT that came out of Facebook, 160 gigs of text data. So that just shows you that this is crazy. And some of these models take like long time to train. I mean, I think even AlphaGo, the one that came out of DeepMind, although it's not released as a pretrained model and everything, but the power of that model is also demonstrated on how long it took to train and how costly it was. So it took 40 something days to train AlphaGo. And the point here is that if you do not have the resources to do this, you'll never be able to train this kind of models, let alone the compute resources, but even the knowledge, the intellectual capacity, and the amount of money you need to afford those things. So it's just really impractical to try and just be a general company that's just out there. Maybe you're an insurance company, and then you really want to do, like, I don't know, tax analytics on your claims or something like that, and you like, you can't afford this type of compute and this type of knowledge to begin with. But the good thing, as I will demonstrate, is that then we can use transfer learning to sort of circumvent those challenges. And the way we do that is that, okay, so first of all, the textbook definition of transfer learning from Wikipedia as it is that you really take you build a machine learning model that will learn something, and then you transfer the knowledge of that model into another model. So traditionally in deep learning, what would happen is that Microsoft would release a model, or Google or Facebook for that matter. When they release the model that they've trained on like large volumes of text that I don't have, and also trained on large compute resources that I don't have, then they release the weights, and when they do, I can take those weights and then train an upstream task that is very specific also, by the way, to my own problem, because I'm taking advantage of the stuff that the model that they are releasing learned throughout the training there, and I'm taking advantage of that, and then I'm bootstrapping my model, and then with small data and very specific domain, I can train a very, very, very competent model that can be ready for production. And that's the whole point of transfer learning, is that you can do that with images, you can do that with text. You can see here on the left, this is like the models that I got from Touch Vision, and this is the models that are ready for you to just start using pre-trained as they are. You can see that you've got like ResNet 18 there, AlexNet, all of these fancy models that have complex architectures that take like a young LeCun to be able to come up with. You can take advantage of that architecture and try to just take your image data, try to retrain the model, and then off you go. You spend more time trying to make sure that this thing can solve the problem that you have, rather than trying to make a model learn how to detect edges, for example. Because much as is minuscule, is a sort of like immaterial ask, the model still has to learn those things, and for you to teach the model to do those things is very costly. So you can take advantage of a pre-trained one where it already knows what an edge is, it already knows how to recognize shapes and other things, and then you sort of start teaching it on your very specific domain, and then boom, all of a sudden you have this image classifier that's really working very well on your own data. And that's the point of transfer learning. It's amazing. So this is TensorFlow Hub, and on TensorFlow Hub you can find a couple of hundreds of models that are already pre-trained by Google and others. Here I'm just filtering on the text ones, but you can find ones for images, for TensorFlow JS, because you can do this on TensorFlow in the browser itself, or you can find these things that are built specifically for TF Lite, as in like building them for mobile devices, edge devices, Raspberry Pi, an Android phone, iOS, that type of thing. You can find all these models, and all you have to do is write code to download them, retrain them on your own data, off you go. For the most part, if the models are already quantized and other things, you don't have to worry about quantization and what. But for the most part, these pre-trained models are meant for you to just bootstrap the amount of time it takes. Reduce the amount of time it takes for you to go from a model with data to a production thing that's built into a product. You can do that by just taking advantage of these models. That's the point. And of course, we can never be able to do all of these things if we all still have to write the code from scratch and do all the painful things. So that's where open source frameworks comes into the picture, especially things like wrappers. So one of my favorite wrappers are on the right, but here we're looking at the common, or the top 4, if you like, open deep learning frameworks out there. That will be your TensorFlow, PyTorch, Keras, and FastAI. In actual fact, Keras has since been merged into TensorFlow, so now you accessing Keras via the TensorFlow backend. So you could say that TensorFlow and Keras are sort of the same thing. So we're left with TensorFlow, PyTorch, and FastAI. And of course, PyTorch has been this is a bit outdated. I got it from a blog post on KD Nuggets that I left here, and it's just a nice visual that just shows what's going on there in terms of stars and forks and watches and contributors. But the important thing about this is that people are busy maintaining open source platforms. People are busy maintaining open source frameworks that really, really just require you to work, to use. And when you find something that's limited or is not working properly, you change it. You customize it the way you want it. And well, for the most part, when it works better, you can even push it upstream with a pull request, and then they can say, okay, this works nicely, let's merge it to master, and then other people can use your own modifications. Or otherwise, you could just use it as is, or change it the way you want, and then just use it on in your own organization. So the power of open source is exactly that. You can get the code, change it, do it the way, make it do what you want it to do, but without having to write the code from scratch. And then there's wrappers which sort of make it very high level. These are just some of my favorite. Transformers, obviously, and Transformer is not really a wrapper per se, but it does wrap some kind of things. It sort of abstract the complexities of having to write the painful code to get these models to work, but it's not going as high level as others, especially the ones that I listed with here. The Pavlov goes a bit too high level, where you just have to work with the config file to get the models to work. And simple transformers, this is one of my favorite, where you really just go from a pandas data frame, and then the abstraction is like amazing. And then you have K-train. This is also very nice, especially for retraining stuff and other things. This is just examples, and I think I left out Spark NLP, which I later use in my presentation. But Spark NLP is also similar, just doing these things on Spark. But the point here is exactly that. So transfer learning. I'm going to talk a bit about what is unsupervised pre-training, especially that we're sort of making the context a bit NLP. So what is unsupervised pre-training in NLP, and what are we seeing coming out of the NLP race that we haven't seen before, to be honest. So let's start there with unsupervised pre-training. So unsupervised pre-training is a technique where you sort of take a large corpus of text and train a model to do tasks that don't need to be labeled. Like, for example, the Andrew here did trained an LSTM to predict the next the sequence that comes next, right? So you can imagine you have a sentence, and then you train an LSTM to say that I'm gonna predict that in this sentence this word will come next after this one, blah 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 blah. But as and when you do that, you learn important things about the language, and the things that you learn about the language, importantly, once the model can generalize very well on your training and validation set for that task, then you can take that and say, but what about this task, and what about that one, and that's the whole point. And we saw OpenAI use this in GPT, but in their earlier version of GPT, I think they use a combination of techniques, and the GPT-2, they were just predicting the next sequence to say that given that you have the following sequence, what is the next word? What is the next word? What is the next word? And that's why OpenAI in general is so good at generating language, because it was trained to generate the next sequence, if you think about it. But BERT was a bit different. BERT did something quite clever, although it wasn't new, but it's very clever. It's in a sense that they said, okay, cool, instead of just training from left to right, we also want to train the left context, to say that I don't want to just generate the next sentence, but I also want to be able to mask some of the words in the entire corpus, and let the neural net or the model, the language model, sort of learn to predict what word should go in that mask. So you can imagine if I have a sentence called I love NLP, and then I remove love with a mask, and I say predict what I mask NLP should be saying, and then the model should know that it should be love. But when the model is learning that, it's obviously learning a lot about the language, and that's what we want. BERT is also trained with another a task of predicting the next sentence. So given that you have a bunch of sentences, we randomly 50% of the time remove the next sentence in the corpus and replace it with random stuff, but then keep the ones that are true, and then our prediction problem becomes, is next sentence or is not next sentence, in a binary way, to be honest. But when you're training that model that way, it learns a lot of the out of the language, and then you can take the learning out of there and then bootstrap it into another model, initialize some weights, and then off you go into other different types of tasks. And that's the point. You think about it as like unsupervised pre-training, as you're teaching the model, you're giving it knowledge about the language. That's it. So the model now has knowledge about the language, and then once it does, you say, cool, now that you know the language, can you please solve this very language specific problem? Like telling me whether two sentences are a paraphrase of each other, or as when I start typing hello there, I am, predict what I'm going to type next given the context of this of this email. This is what you see in instant reply or smart reply in Gmail and other things. I mean, the point here is that once you have all these tasks, you can be able to train language models or models on your, can be able to transfer these models into your own domain specific problems, deploy them, and then integrate them into your products. So look at the NLP race. Most of these people use transformers and all what I mentioned. In actual fact, I omitted to mention something very important. BERT in itself uses this technique. It's called word pieces. So BERT was trained on word piece tokens. Word pieces are very important because they also introduced a very clever way of language modeling, where you just sort of so it's sort of like it's a very clever technique of handling tokenization. Unlike the past, it uses tokenization in a very unique way of just of substituting some of the words in the thing with in the whole corpus, and then making sure that your language model can generalize very well on new things because of how you've broken those words into pieces. But it's a big topic on its own, so that's what you have to know. But most of these things are using that technique, and you can see here Also another problem. This is the glue leaderboard. So the glue leaderboard is made up of tasks like MRCP, STS. This is SST as well there, and then you've got your MNLI. You also have your squad. So the idea here is that once you train your language model, we give you a test set, and then we want you to tell us how well does that test set do on the following task. And for the most part, these guys train a single language model and then try to fine-tune it on the multiple tests and submit here. But you can see that there's no democracy here. I mean, you've got your Google, your Baidus, and then your Alibabas, and it's like, you know, at least you have Stanford there at number 13. But if you look at this is just a demonstration. I mean, your Facebooks are there. Microsoft is just a demonstration of who has the most compute power, who has the most resources to train these models. But the good thing is, once they train, we can take advantage of them using the transfer learning thing, as I said, to try and just do it. Poor as we are without our resources, without our data, without our skill set, we can be able to just transfer learn from whatever it is that they did and then try to train on our very own specific domain problems. So now I'm gonna just do a demo slide. I mean a bonus slide here for the demonstration with code of what I've been talking about. We're gonna go through question answering, text summarization, sentiment analysis, text classification, image classification, and I'm also gonna give a bonus slide for the Spark people. I know that there's a bunch of people who really live and use Spark for everything, so you can also see how you can take BERT into Spark very quickly. So in here we're using what this is completely off the shelf, using transformers pipelines. So transformer is a library from Hugging Face. Find it on YouTube. I mean on GitHub. Sorry. So using transformers, we can take advantage of this cool thing they have called pipelines. And pipelines allows us out of the box to do inference without doing nothing. All you have to do, tell it that you want question and answering, give it context and questions, it answers. For example, for text summarization, give it a long passage and then pass some few parameters there. What is the length of the summary that you want, blah, blah, blah. And then you get a summary of that. You have to do nothing. All you have to do is just write this code and it just works. Sentiment analysis, very common application. This model, very accurate. I got shocked myself when I was trying to train it on my own. I mean, when I was trying to do inference on my own data, working surprisingly well. So take advantage of this. This is an example again with K-Train. K-Train also, like when you want to quickly have new data and you want to quickly use, let's say, BERT or something like that, and then you just want to sort of very quickly take that and train it on your new data. You can do that with K-Train with this few lines of code in Python, and you can see this is really few lines of code, but what you get out of this is a very effective, very competent model that you really can use on your own data or in production. And the point is just to demonstrate how slick this code looks, how small, and obviously remember that the important thing though is that you have to understand what you are doing here. You know, what is this max features, what is this max length, what is this n-gram range? You have to know what you're doing here, because if you don't know, then you don't know what you're training. But that is why it's important for you to say, I figured out the research paper. Once you figure out the research paper and you know what the model that was released is doing, once you have all that detail, it shouldn't be painful for you to now start using that detail that you know into your own data and trying to go to prod. The point is that you can use all of these tools, given that it is conditioned on the fact that you know what the research paper is talking about, because these tools assume that you have a lot of high-level language. There is a very big abstraction here. So if you're not comfortable with what the models are doing, blah, 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 then the abstraction will take away your ability to understand this anyway. So you really have to make sure that you've got a bunch of people who understand what the models are doing, and then you can say that now that we know, how can we try to apply it on our own problems? Because you know you have problems that are similar that you know you can apply to these things. That's the point. I mean, you can do a similar thing with images on the right here, just showing you how you can do this with images. Just I'm just loading pre-trained ResNet 50 weights there. I'm freezing the first 15 layers, so I don't have to train them at all, and I train everything else after the 15 layers. This is a bit debatable. Some people want to choose other ranges here, but it doesn't really matter. You have to do some research as to which one will be ideal and which one will be the best. But yeah, that's the point. By just writing this small code, you have an image classifier that you can train on new images that can do surprisingly well, and on new text that can do equally surprisingly well. And of course, if you are a Spark person, this is a very clean, very small code in Spark that gives you out of the box a pre-trained universal sentence encoder embeddings that you can now just start using. I'm getting them from TF Hub there, as you can see. I'm using the large model. Then you use those embeddings, and then you train them on your own. You retrain on your own data, and then you start predicting. And that's just how easy it is. And the point of this talk is just to demonstrate that. But remember, you have to understand what the models are doing. These tools are meant to abstract away the painful code, assuming that you know what you're just trying to achieve. It's super important, because otherwise you've got a bunch of people who are just writing code that looks like it's working, but the model is not doing whatever it is that you want it to do. So you really have to figure out, you really have to have the context of what does USE do, because then you can know how to and where to apply it. Okay, so that's it. You can get in touch with me on the channels listed here, but what I did as well is that I left the code for you guys here. So if you're gonna get your hands on this presentation, you can click on this Colab. You'll find a Colab notebook here. All the demos I was showing you here, I'm using them on real data, some on Kaggle competitions, and then I'm making submissions there just to prove to you guys how you can use these models. Easy as it sounds, most people would be very skeptical to say, I don't think this will work. But I'm just trying to demonstrate. I mean, if you demonstrate that a model works with the Kaggle competition, you can pretty much try to work very hard to make sure that you package that model nicely into a production pipeline and deploy, and then get customers using your model, or maybe complaining for the first few iterations. But the point is, if you do sufficient research, you don't have to think about the rest of this stuff. Thank you so much.